Okay, so we're continuing on here. We're going to talk about relative or local extrema today. So, relative and local. Notice there's not parentheses here. You have to state that. If I just say extrema, I'm talking about those absolute or global ones. So, if there's an open interval containing some specific point, then that point can be a local or relative max if you look to the left, you look to the right, and there are no y values greater than that one. All right, so same thing, a value, that x value, if you look to the right and to the left of it, if there are no values smaller than that y value, then it's a local minimum. All right, so it's better to see an example of that. But we have a theorem here. Relative or local extrema can only occur at a critical value on an open interval. This isn't saying that there is guaranteed to be one, like the extreme value theorem. Okay, it's just saying that those are the only possible places where they can occur. And there's another note here. In this class, we're going to decide that relative or local extrema cannot occur at the endpoints. Okay, that's why I'm talking on open intervals. All right. So identify all the critical values of the graph of g of x, then determine whether there's a local max, local min, or neither. All right, critical values. We're going to say this would be a critical value because that's a place where the derivative 0. Here's another one of those. Here's another one of those. All right, and then there's nowhere else where the derivative 0, but it looks like right here the derivative would be undefined. All right, so then these values are potential relative maxes or mins. All right, so we would have, this one would be a relative max of f of b at x equals b because there are no y values to the left or right of it that are higher than that one. All right, up here we'd have a relative max of the y value f of d at f of x equals d because there are no y values greater than that point. All right, down here we'd have a relative minimum of f of c at x equals c because there are no y values lower than it in that immediate area. It doesn't matter that these are lower. We're just looking in we're zooming in on a specific area and saying, are there any y values lower than that? And in this case, there aren't. So then here we'd have a relative minimum value, all right, of f of e at x equals e. Now, can we say that there is a relative max here? Absolutely not. Okay, it cannot occur at the endpoints. All right, relative extrema may not always be at nice, tidy hills and valleys, just like the last example. So we got to pick up this master example here. Oops. The graph of h of x is given below. Find all the critical values. And remember, that's where the derivative equals 0 or it's undefined, okay, on the interval, and then determine if a local max or min or neither occur there. All right, so I'm just going to say right here at this value, the derivative would be undefined because it's not continuous. Same thing here, 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 okay? At all of those places, the derivative would either be 0 or undefined. And remember, we are not including our endpoints for local maxes or mins. So at x equals 3, this point right here, I would say f of, there's a maximum value of f of 3 at x equals 3, negative 3, sorry. The reason why this is a maximum is because if you look to the left and look to the right, there are no values greater than that. All right, so how about this point right here? Look to the left, we have values that are lower. Look to the right, we have values that are higher. So this is neither at this point. All right, then we have this one. This is, we have an open interval here, an open interval there. So that's neither. There's nothing happening there. And then we have this. If we look to the left, there's values higher. If we look to the right, there's value higher. So technically, we have a minimum of, we could say, what's that, about 0.8? Well, let's just, we won't guess. F of 2 at a value x equals 2. If we wanted to have an absolute max or min, okay, if we said this was, we were looking at an absolute max or min, we could say that there is an absolute minimum value here, because nothing's lower of f of -4 at x equals -4. And if we wanted, we could say that there's an absolute max of, all right, let's just say that's 2 on this interval from -1 to 1. Find the critical values of each of the following functions. So critical values, remember, occur where the derivative is 0 or it's undefined. So first thing we need to do here is find the derivative. I don't know what this graph looks like right now. I could sketch it, but I could just look at the derivative. So using the power rule, we'll take the derivative. And we need to find out, is that ever going to be undefined? It's not, because it's a polynomial. So we just have to look where the derivative would be 0. All right, so I can factor out an x. And then I believe this would factor into 2x plus 1 and x minus 2. So that means that my derivative is 0 at x equals 0, x equals -1/2, and at x equals 2. So these are my critical values, 0, -1/2, and 2. Okay, we're going to use those to evaluate different things later, but you have to be able to find them first. All right, this one, I don't really like taking the derivative of absolute value functions, so I'm just going to sketch this graph here. 2 minus this, so it means I'm going to take that basic absolute value shape and flip it over, and I'm going to move it up 2, and I'm going to move it to the right 4. All right, so it would probably look something like this. So this is our g of x function. So if you try to determine where the derivative would be 0 or where it would be undefined, it would be right there at that point. So that is our 1, 2, 3, 4. All right, so the critical values would be at x equals 4, and that's because the derivative would be undefined there. All right, and then we have our last one. Might as well take the derivative. Now be careful with this one. All right, we have to use the product rule. All right, I want to make my pen a little skinnier here. There, okay. First times the derivative of the second plus the second times the derivative of the first times, this would be 3/5 x to the -2/5 power. All right, I'm just going to rewrite this here. So I would put negative. Let's see, should I distribute that? I'm going to say maybe not yet. We're going to do one of your favorite things coming up. We're going to factor out least powers, because it's good to practice that. All right, so the least power here is x to the -2/5. So I'm going to take that out, x to the -2/5. Okay. So we have to put what's left over. All right, I'm going to write over here, side work. I'm going to even label it so you can know what I'm doing. All right, side work. So I'm trying to think, x to the negative 2/5 equals x to the 3/5, actually it's negative, times what? All right, what would I have to multiply that by to get negative 2/5? And remember, when you're multiplying exponents, or multiplying something, you add the exponents here. So it's going to have to be negative x to the 5/5 if you want to get negative 2/5 here. Okay, made a little mistake here. Forgot I put that in the wrong spot. So we have 3/5 and negative 2/5. Negative 2/5, that power times what? All right, let me just erase this. I don't want to freak you guys out. All right, so let's start that over. Okay, so we have over here, little skinny pen. There we go. All right, x to the negative 2/5 times what will give us what we wanted, negative x to the 3/5. All right, and that what's going to have to be x to the 5/5, and we want to make it negative, so we match that sign. All right, so an x to the negative 5/5, that is the same exact thing as x to the first. So then when we write this over here, the only thing that's left here will be a negative x. And then the only thing that's left here will be 3/5 times 4 minus x. All right. The reason why we want to do this, because now I can rewrite this, because this has a negative exponent, okay, I could rewrite it like this, negative x, and then sure, we could distribute that out, it won't hurt us. 12/5 minus 3/5 x. Oh, we can even combine that a little bit more, but not right now. If I write it like this, it's easy to see where the function equals 0 and where the function is undefined. All right, so let me rewrite this one more time. Negative x minus 3/5 x, well, that's really like 5/5, right? Negative 5/5 plus negative 3/5 is negative 8/5 x plus 12/5 on the top and x to the 2/5 on the bottom. So where is my derivative equal to 0 at? All right, well, that's where if the numerator will be equal to 0. So then I can just move this 8/5 x to the other side, multiply both sides by 5, and then 12 divided by 8 can be reduced. Divide them both by 4, so you get 3/2. So x equals 3/2 is a critical value. Then we need to look at where our function is going to be undefined. Our derivative. Where's our derivative undefined? Well, that's where this would be 0, and that's going to be at x equals 0. So we have these two critical values right here. All right. And if you look at the graph of this, okay, go ahead and grab your calculator. Look at the graph of this. This is where we have a horizontal tangent line. And the derivative's undefined there, horizontal tangent. And this is where we have a cusp. So our derivative's undefined there. I mean, our derivative, yes, we have the derivative equal to 0. All right. So these are two of our critical values. And when we plug them into our function, they might be our absolute mins or maxes. All right, so now we have a way to analytically determine them. All right, but let's just look at this here. To find the absolute extrema on a continuous function on a closed interval, the steps that you should take are identify the endpoints immediately. All right, identify any critical values. All right, remember that they have to be in that interval, and that's where the derivative is equal to 0 or it's undefined. And find the function values at those endpoints. Whatever the biggest one is the maximum, whatever the smallest one is the minimum. All right, think about it like a contestant. Super excited right here. So you're a contestant on this really Fun game, Extrema. Alright, so if this redheaded person is the endpoint, her Y value is 3,120. Here's a critical value in the middle. Here's our left endpoint. Here's our right endpoint. And our critical value. Which one of these is the highest? Okay, that would be our right endpoint. Look at the Y values. Which one's the lowest? That's our critical value. And then the left endpoint gets a green ribbon just for participating in our silly little game there. Alright, let's see, I think this will be the, how much time? Oh yeah, this will probably be our last one here. Determine if the extreme value theorem applies. So this is continuous everywhere, so it's going to be continuous on this closed interval. So yes, it does apply. The function is continuous on the closed interval from -1 to 2. If so, find the extrema. Alright, so the extrema can occur at the endpoints. Find them immediately. Alright, so we get -1 to the 4th is just +1, so that'd be 3. -1 to the 3rd is negative, plus 12, that's going to be 15. F of 2. Okay, 2 to the 4th gives us 16 times 3 is 48. And then we have 2 cubed is 8. So negative 12 times 8 would be -96. Add those together and we get -48. Alright, the only other places we check the endpoints, we're good. Now we need to find out where the derivative is equal to 0 or undefined. Alright, so take the derivative, 36x squared, find out where it's equal to 0. It's not going to be undefined. It's always defined. Alright, so we aren't going to have any undefined values. So if I take out a 12x squared, I'll get x minus 2. So our critical values are at 0 or at 2, I think, right? 12 times 2 cubed minus 36 times 2 squared. If I plug 2 into there, I already did. So we have -48. If I plug in 0 to my function now, remember your regular function, we're going to get 0. So take a look at these values here. Which ones are which ones are our absolute maxes or mins? So we're going to have a maximum value of 15 at x equals -1. That's the highest. We're going to have a minimum value of -48 at our x value of 2. And then f of 0 gets a green ribbon just for participating. Yippee. Alright. So there we go. That's the end of our video. So you're happy too. See you in class.